All right, here is how our Cloudera Manager portal looks like. You can see on the list of services that we have more or less all the ones that we mentioned during the presentation. Specifically, we can see how our cluster has running instances of Flink and SQL Stream Builder, which, as we said, make up the CSA package of CDF. Then we have Nifi. We do not have Nifi registry at the moment, but Nifi is representing the CFM package. We have Kafka, which also, as we said, is included already in the CDP runtime. And together with Kafka, we also have SMM, or Streams Messaging Manager, which is a nice UI to monitor and manage the Kafka cluster, and which you will be briefly looking at during the day. So now let's have a look at the service which will be the main focus of our demo today, and that is SSB, SQL Stream Builder. First of all, if we look on the left side of the screen, we can see three different sections that we previously mentioned. One is the SQL console, and then there is the data provider and the materialized view section. The SQL console is the one that we see first thing when we open SSB. And as you can see, the main element of this console is a SQL pane. And this is where we actually write our queries on bounded or unbounded data. Every query that we run actually triggers a Flink job. So we also have a job name randomly generated by the service, but also editable as preferred. We have a sync, which right now it's set to none, which means that if you run a query now, the results will be displayed as a sample on the screen. However, we can actually select different types of sync, like Hive tables, Kudu tables, Kafka topics, and so on. And we're going to see different examples of this during this day. And at the end of this screen, we also have the logs tab and the results tab, which is where the sample results is actually displayed once the query is running. Right now, there is no sample, but as we will run the queries during the demo, we will see the data actually coming out up here in this section. Let's move now to the data provider section. Here, we find all the connectors that allow SSB to read data from different sources or to write data to different things. As you can see, we have Kafka, Hive, and Kudu already set up. Kafka and Hive are automatically set up by Cloudera Manager, provided the SSB is correctly installed with the Kafka and Hive dependencies. So you have them right out of the box without having to worry about anything. However, as you see, we also have Kudu, and Kudu is a manual addition. It's actually a fairly easy task. You just have to click on register catalog. You have to pick a name for your new catalog, for example, Kudu in this case. You have to select the type, for example, again, Kudu in our case, and then you have to add properties. And in this case, the Kudu master address and port is the only thing that's needed. You saw there were other types, for example, schema registry and custom. However, right now, we're not going to be focusing on them. There is extensive documentation available online if you want to experiment with them and so on. The third section is the materialized views. Again, this is not going to be the main focus of today. However, just know that this is the interface where you can manage and monitor, let's say, all the API that you define when you create a materialized view from your queries. Now back to the console. Once we saw the data provider, we can actually explore the table section, in which we can see the tables that effectively are available for us to write to or to read from. First thing that we see is a list of Hive tables. They are coming from the Hive catalog, so the Hive data provider. And as we move on in the list, we also see different types of catalog. For example, there is the Kudu catalog, and also there is the Kafka catalog. Now, the Kafka type is a representation of a Kafka topic, and is what effectively allows us to query such topic as if it was a table. We can have a look at an example now. First of all, let's note how Kafka tables can actually be edited and deleted, whereas Hive and Kudu tables are coming as they are automatically from the data providers that we define. So if we want to modify or add a Kafka table, we have to do it manually, but we cannot manually change what we see in the Hive and Kudu connections. So now we're going to look at the first example, and to do so, we're going to first see how we are populating a little Kafka topic, and then see how to create a table on top of it and to query it. So let's go to Nifi, where our little pipeline is running. As you can see, it's a very easy pipeline in which we are just pulling data from a public API of currencies, cryptocurrencies and normal currencies. We are manipulating the response a little bit, and then we are pushing it in JSON format to a Kafka topic. The Kafka topic is called rates, and we can actually see it in the Streams Messaging Manager UI. Now, this is the nice recent addition to CDF, which allows us to have a panel over Kafka, where we are able to monitor and manage all the topics, producers, brokers, and so on. So you can see we have some nice information on the top. We have a view of all of our topics, and especially we can even dive deeper into the different sections and, for instance, see some metrics about our cluster, metrics about the topics themselves, and even create or delete, if we need, new topics for our cluster. So specifically in our case, we want to look at the rates topic. We can already see that it's being populated with data. We can see some metrics about it and its state, and then we can explore it. Again, we have additional information about the topic, and we can see the data that is contained inside it as it populates it in real time. So as it flows through the Nifi pipeline. Specifically, we can see that every message is a JSON format, is in JSON format, and it contains a certain amounts of fields, namely ID, symbol, currency symbol, type, and rate USD. So we have a topic that is being filled live in real time with the Nifi pipeline. Let's go to Stream and SQL console and create a table for it. We're going to add the table. It's going to be a Kafka table, of course. We're going to give a name to it, which in our case will be rates. We're going to select a Kafka endpoint, which is nothing but the pointer to the Kafka data provider, which was shown a few seconds ago. We're going to select a topic name from this drop-down list. All the topics are automatically detected, and we just have to select the one that we want. JSON format is the right format for us, and then we have to define the schema. Now, we could do this manually, but luckily for us, since the topic is already populated, so it contains certain records, we can detect it dynamically. So we're gonna wait for SQL Stream Builder to find the right schema for the topic. There we go. And as we can see, the names of the fields are exactly the ones we saw in the Stream Messaging Manager UI. So we have an ID, we have a symbol, we have a currency symbol, we have a type, and we have the rate in US dollars. We're going to save our changes. We have our table here, and now we can go back to the Compose tab and run our first query. Let's go back to the Compose tab, and we can run our first query. So as you see, this is nothing but SQL. It's just a select statement utilizing the rates table, which is the interface to our topic. Sync is set to none, so we just expect the result to pop up in the results tab in the form of a sample data. And as you can see, this triggered Flink job, which will now display some results in a few seconds. And there you go. This is our data. The stream is flowing and the data is being sampled, but we are actually looking at all the information as if it was a SQL table, just that the data is continuously updated because the stream is actually running in real time. As we said, by the way, this is Flink job. So if we go to the Flink dashboard, we can also see the job running with the same name that we defined in the SQL console, and we can monitor it as if it was any other normal Flink job. So there is no difference here. All right. Of course, we did a simple select statement right now. We can edit the query as if we would with any other SQL query. For example, we can select just certain columns instead of all of them. Maybe we want to see something like this. We can run a query again. A new job will start, and eventually we're going to see the results coming on the screen with just the subset of columns that we define in the select statement. There you go. You see ID, symbol, and rate US dollars. Everything as if it was a SQL table, but we're actually querying a Kafka topic. Now, this is a query on unbounded data, and it's extremely cool. What's actually even cooler about SSB is that it allows us to mix and match unbounded and bounded data seamlessly. So, for example, we can join a Kafka stream with a static table, maybe in Hive, maybe in Kudu, and so on. In our case, we're going to run another example now, and we are going to try to join the live currency rates that we are getting from the rates topic with some master data about currencies that we have in a pre-populated Kudu table. So let's try another query. Let's first have a look at it. This is nothing but SQL again. We are simply joining two different sources. One is the rates topic that we just saw, and another one is a table in Kudu, which is called rate assets Kudu. This is just a table, as we said, with master data about currencies. We can actually have a look at it in Impala. So we go to U, and we can select it and see its content. There we go. So again, you have an idea about the currency, then you have additional information, website, supply amount, and so on. And we also can see the schema on the right. Of course, the schema is holding the information that we see here, and is the one that we will see in our query when we actually select certain columns. All right, so we are applying a filter in the end, but this is nothing but a SQL query. So let's run this. Another Flink job is started, and we're waiting for the sample results to show up in the screen. There you go. You can see all the information here displayed in the results tab. We have columns coming from the Kafka topic together with columns coming from the static Kudu table. And this is the result of our join. As we saw, it's very simple. We are actually doing a very complex task in just a SQL sentence, and it's an extremely powerful application of this service. So far, what we did was just pure SQL. However, as we also said in the introduction, we are actually able to apply certain Flink-specific functions in order to perform some time-based logic and a bit different computation on our streaming data. We can have another example of that, in which we use the window function. Now, this window function will look very familiar to those of you that know how windowing functions work in SQL. As you can see, we are partitioning by ID, we are ordering by a timestamp, and we are specifying a range, a time range, which is 1 minute. So what we are actually doing in this query is that for every minute, for every ID, so for every currency, we are trying to calculate the minimum and maximum rate. So what we expect in the results of this query is to have the current rate, and next to it, the minimum and maximum of the past minute for that specific currency. In order to visualize it properly, we're also filtering by a single type of currency, but that's just for our visual, ease. So now the display will appear with the results. We're going to see how this information is actually changing in time. There we go. We see information about the Dogecoin with the current rate in US dollars, and then the minimum and maximum rate, which are changing, as you see, and they depend on the previous information. So the sampling is continuing, and we see the information changing again. And everything depends on what happened in the past minute. So all of this is extremely nice, once again, but the main question you are probably asking yourself is, okay, what do I do with this data? Once I see it displayed in the results section of the screen, it's very nice, but I actually want to store it somewhere. And of course, as we said, this is possible. We can do it thanks to the sync option that we have here. So far, it was set to none. We're going to see now how we can do it with different types of target tables. Let's run an example. I'm going to try to save the result of a query in a Parquet table, which I previously created. This is a query very similar to one that we just ran a few seconds ago. However, there are two main differences. One is that I'm actually joining with master data from Hive, not from Kudu, but this is just to give you a glimpse of the different combinations that you can do in your queries. The main, the most important difference actually is this little piece of syntax here. Now, without going into the technical details of exactly why this is happening, let's just say that this piece of syntax allows us to effectively write the result of the table of the query to Hive. If we didn't put it, we will still have a running query. We will still see the results being displayed on the screen. However, Flink will just create a single chunk of temporary data in the HDFS location of our Hive table, and this data will never be committed. So effectively, we will query our table, and the result will always be an empty table. If we add this, we are basically helping Flink to be able to commit these partitions of data and to effectively fill the Hive table. Now, with this said, let's have a look before we run the query at the target table that we have in Hive. So let's go to our Hive SQL Builder, and let's have a look at this table here. So it's called demo rates join sync external parquet, and this is the scheme on the right, and we can confirm that it's actually an empty table. If we run the query, there you go. You have 0 results. The scheme, of course, needs to match the one that we plan to have in our results in the query. But as long as this is happening properly, we can select it in our sync here. So let's actually pick it. We have many syncs, but the one we want to use right now, it's this one. And finally, we can execute our query. So we are still going to see the results appearing in the screen as a sampled data. However, at the same time, this data is also going to be written to the sync that we define. There we go. So we see the results here. And if we go back to Hive and we select from our table again, there you go. You can see the data being written in real time to this parquet table. Again, this is a very powerful application. We are just doing it with one simple SQL query, with just a very, very small addition to the syntax. But we are joining a stream with a Hive table and writing it in another Hive table in a matter of seconds. So that's a very powerful application of this service. Finally, in the last example, we are also going to see how to write the results in Kudu. So we're going to see another type of sync, and we're going to do it with a query using a different type of Flink time-based function, and we're also going to do it running on a faker table. Now, the faker table is a type of table that you probably saw earlier while I was showing you the tables tab. And just like the data gen type, is nothing but Flink specific type of dummy data generator. So essentially, when I have a faker table, this table is generating dummy data based on certain libraries and information available to Flink, which is just creating fake records depending on certain parameters. For example, we are now going to have we are now going to run a query which is based on this table here called spellscast. And as you can see from the description, it's just an example based on the Harry Potter world. So for those of you that are familiar with this with these characters, we're going to see just spells cast by wizards, and we're going to try to query this information in a nice way. So the query we are going to run is this. And we're going to use the TUMBLE function provided by Flink. The logic is pretty straightforward. We're just going to count for every 10 seconds. So the interval defined in the TUMBLE function, for every 10 seconds, you're going to count the spells, the expecto patronum spell cast by a specific wizard. Being a Kudu target, Kudu, of course, as you probably know, is based on keys. Our key in the final table will be the wizard. So every record will be absorted to the target table, which means that every time we query the table, we're going to see for every wizard the latest available information about the number of times this spell was cast in the last 10 seconds. Let's make sure we select the right thing, which is a table that, again, I previously created. There you go, it's this one. And let's run the query again. It's this one. Yeah. Let's run the query again with the right target. Job is successful. We're going to see the results coming up on the screen soon. There you go. They're starting to come, of course, with different sampling logic depending on the tumble interval that we have. But the query is running, so we can go back to Hue. We go to Impala because we want to run a query on a Kudu table, and we can just select. As we expected, we have a list of wizards. The spell is always the same, but the times cast is actually being absorted every 10 seconds. Of course, absorted means if the wizard is already there, present in the table, the times cast column is going to be updated. Otherwise, if it's not existing, a new record will be inserted. So every time I run, provided that 10 seconds have passed since the previous time, I should be seeing different numbers here. Of course, this table is being updated live, but nothing prevents me from querying it as if it was any other table. So I can order by times cast, for example, and see which wizard has cast this spell the most times in the previous 10 seconds. And if I do it again, it's probably going to be a different one.